Hello, here you can see a spinning 3D ASCII donut. No 3D engine or ray tracing is used here. The original donut code is created by Andy Sloan. He explained his C code in his blog post. I will go through his blog post and explain key details necessary for creating an ASCII donut, and after that we will write the code in Python with Pygame. What I found unique about this code is not that the original code is formed like a donut and then create a rotating ASCII donut, which is already impressive, but the approach used here. If I run a donut animation, you can see how the donut is spinning and characters are changing, imitating the illumination. But no 3D engine or ray tracing is used here. So how it's done? It uses several cool tricks and some are already visible to us, we just need to focus. Let's focus on just one character. First, you can see that character doesn't move, it just changes and stays in the same position. And every other visible character doing the same, forming the donut image. If we slow the animation, we can see that there are 12 changing characters, which represents illumination, from dimmest to brightest. So what we see is a screen made from character pixels, and every pixel can get 12 different character values. Okay, but we are seeing a 3D donut, so how to project it on a 2D screen? Let's start with this diagram. Here you can see a viewer looking at a screen and seeing a 3D object behind it. To project a 3D object onto a 2D screen, we need to project each 3D point. And this is easier than you think. You can see that we have two similar triangles with relative proportions. So if you know a donut radius, the distance from the screen to the viewer, and at what distance the donut is from the viewer, we can calculate the radius of the donut on the half screen we want to see. In the code, we will use this proportion to calculate the distance from the viewer to the screen. Let's move down in this block and start with animation. Here you can see a 3D spinning donut made only with points, no ASCII characters and no illumination. This is how a donut looks with only a projection. What can you notice that the donut is seen through? We can see all donut points and we want to see only points which are closer to us. So this is another problem projecting a bunch of 3D points on a 2D screen, which is to plot only closer points to the same location on, in our case, a pixel. I think you already thought about how to solve it, we just need to track Z coordinate. So if we have multiple projected points to the same pixel, we plot only points with lower Z values which are the closest to the viewer. But how to draw a donut or mathematically called torus? Let's move up to this drawing. First we draw a 2 distance from the central axis a 2D circle with the radius r1, and second we rotate the circle around the central axis. For that we will need a rotation matrix. After rotation we will get a donut made of points as we saw before. And to make a donut rotate on at least 2 more axes, we use another 2 rotation matrices. This one rotates around the x-axis and this one rotates around the z-axis. And that's almost it. What's left is to calculate luminance and assign corresponding ASCII characters. To calculate illumination, we need to know the surface normal, the direction perpendicular to the surface at each point, and light direction. The light source is chosen to be behind and above the viewer. Knowing both, we calculate the dot product. If the product is more than 0, the surface is facing the light. If it's less than 0, it faces away from the light. The higher the value, the more light falls on the surface. And here we get the final luminance formula. And that's it. We just need to put all math into the code. I divided all code into 7 parts. We will start with Pygame window preparation, then we prepare our pixel screen. After that, we will create a donut, make it rotate, add ASCII characters representing illumination, do some tweaking, and finish by making the donut change its color while spinning. So let's start. We will use Pygame library, so please install it before starting to write the code. So to start, we will need 2 libraries, OS and Pygame. Also, let's define some colors, white for our object and black for background. Next, we center our Pygame window on the screen with this line. Also, we need to define Pygame window resolution, width and height. Let's make it 1200 by 1000. And add frames per second, 60. Most likely we won't even reach this number, but it's great to have it. Next we initiate the Pygame, create the Pygame screen with defined resolution, and initiate the clock to track the frame rate. We can also add a caption to our window. Let's add donut. Next we create a while loop where the code will be run. Here we define our frame rate, fill Pygame's window with black color, leave a place for future code, add display update method to be run for every while loop's iteration, and finish with Windows closing part. Here we check for Pygame events. If we have an event of pressing the Windows close button, we stop the while loop and close the window. We also add another event type key down. If we press the escape button, the window will close too. And that's it, let's test it. We have a black window with a donut name in the top left corner. We can close the window by pressing the close button. And if we run the code again, we can close the window with the escape button too. Okay, we have a window. Let's create a function to show a text on it. First we will need to define the font we will be using. Let's use system font Arial with a size of 50 and make it bold. Next we can create text display function. We will need 3 inputs, character and XY coordinates. We create a new variable text, which we assign to the font render method. Here we make sure to convert our character to a string and define color white. Next we create another variable textRect and use the getRect method with a parameter center equal to x and y coordinates. It will get the center coordinates of our rendered text. We finish by splitting our rendered text and defining coordinates, making it centered. What's left is to display some text. Let's move to while loop and instead of code command, we call text display function, where we define that we want to show donut text in the center of a screen. And that's it, we can run the code. We have a centered donut. Let's move to the next part. In this part, we will create our pixel screen. Let's start by defining some new variables. We will need pixel width, let's have 200, pixel height, let's make it 202. We also need some starting values to track our pixels on the screen. Let's create x pixel equal to 0 and y pixel equal to 0. Next, let's calculate our new screen's width, height and screen size. Let's comment a while loop and print screen's width, height and size. So we have a screen width of 6 pixels, a height 5 pixels, and a size of 30 pixels. For now it will be enough to demonstrate the process. Let's go back to the code, delete the print line and comment the while loop. We have a screen made of pixels, but we want to fill it with characters. For that we will add some new code lines. Let's move to the while loop and delete text display function's call. First we can create a list and for every pixel add a char. It's very easy to do. We create a new variable output, assign it to a list in which we have a char and multiply it by screen size. Second, we need to calculate coordinates where all pixels are located. We can do it by writing 2 for loops and looping through screen height and screen width. Okay, so first we loop in the range of screen height and add starting y pixel value to the pixel height value. That way we will move on rows. Next we loop in the range of screen width and add to starting x pixel value the pixel width value. That way we will move in columns. When we finish the row, we need to go to the next column. So we reset x pixel to 0 and when we have a new column, we reset y pixel to 0 too. And finally, what we need to do is to display a character on the screen from our output list. We add text display and in brackets add output and square brackets k. We will add it in a moment. And the pixel's coordinates x pixel and y pixel. Okay, so k will count which char we need to display from our output list. We will display chars one by one in order, so k is just a simple counter from 0 to the last pixel. So we add k incrementation after text display function is called, and starting k value outside the while loop, and reset k value after coordinates are calculated. And that's it. Let's test it. Okay, we have a screen filled with pluses. When we have a donut, all characters will be different depending on the luminance value, but we will get to it later. What else you can see that chars are offset from the start by 1 pixel size because we're starting our for loops by adding pixel height and pixel width values. We can compensate for it by subtracting half pixel values from pixel coordinates. Now it's centered. But it's not necessary, because on the final screen we will have smaller pixels and it won't be noticeable, so let's leave how it was before. It's time to create a donut or torus. So as I talked about it at the beginning of this video, a donut is made by rotating a small circle around the central axis. So we need two for loops. One at some distance from the central axis will create a small circle, and another will rotate the small circle around the central axis, forming a donut. We definitely will need some math, so let's import from math library cosinus and sinus. Next, let's make our pixels smaller. The size of 20 by 20 pixels will be okay, and change the font size to 22. Okay, now we need some donut parameters, like R1, small circles or donut section radius, and R2, distance from the central axis to small circular center. Let's have R1 equal to 10 and R2 to 20. We will project the donut's coordinates to the screen, so we need Z backward and Z. Let's rename them as K1 and K2. K2 we can choose as the 1, but K1 we need to calculate based on the screen size. Using similar triangles with relative proportions, we can calculate K1. We have screen height, donut radius, which is R1 plus R2, and distance from the donut to the viewer, K2. Knowing that we want our donut to be 3/4 or half screen size, we calculate K1. Also, we need to check if K1 is less than K2. If not, we will need to change our parameters. Let's comment while loop and print K1. Okay, it's less than K2. We can go to the while loop and add my mentioned two for loops. We'll go in the range from 0 to 2π to have a full circle. So for theta in range from 0 to 628, we'll use an integer of 628 instead of 2π, and with a step of theta spacing. It will form a donut's cross section. And then our for loop for phi in the range from 0 to 628 with a step of phi spacing. It will form a donut. So what we need to define are theta spacing and phi spacing. It will define how dense of points our donut will be. Let's go up and define them. For cross section we can have a bigger value than for all donut because its radius is smaller. Let's have theta spacing equal to 7 and phi spacing to 2. Now we can go back. From for loops you can see that we will have a lot of calculations. So let's pre-compute cosinus and sinus for theta and for phi. Next we can calculate x and y coordinates before any rotation is applied. After that we will have x, y and z coordinates after rotation. For now let it stay in the same position, we will add rotation later. Next we will add a new variable 1 over z. It will help to track which points are closer to our screen. Also, if 1 over z is equal to 0, it corresponds to infinite depth, so we can create a z buffer with filled zeros, which will create our background infinitely far away. And when we have 1 over z value greater than 0, we will add it to our z buffer list, but we will do it later. Next we can calculate projected x and y coordinates. For x it's half screen width plus k1 times 1 over z times x, and for y is half screen height minus k1 times 1 over z times y. We subtract because into the screen y goes down and in 3D we have up. Also we need to make sure the final coordinates are integers. Knowing projected x and y coordinates, let's calculate which position it will be in our character list. For that, let's add a new variable position and make it equal to xp plus screen width times yp. What is left is to put a character in that position. So where we have a donut, we will add an asterisk character. Let's see the result. Okay, it's not very clear because at the beginning we filled all screen with plus characters. Let's change it to blank space. For the donut, let's leave asterisk and run the code. Now we kinda can see a donut, but it is on the side. Let's rotate it by 90 degrees to us. For that we need new x, y and z calculating lines. Let's comment the old ones and add new ones. Let's see now. Okay, we have a donut. We can delete these old lines and move to the next part. We have a donut, it's time to rotate it. To rotate something in a 3D space, we use rotation matrices. We'll rotate around two axes, x and z. For that, we need two new variables, a and b, which will tell how fast it rotates on these axes. Let's define the starting values 0 and 0. Next, we move to donut creation double for loop and pre-compute cosines and sines for a and b. Now we need to update 3D coordinates after rotation by adding rotation equations. What's left is to add incrementation for a and b. We add this before the update method. And we can run the code. Okay, it works, but it looks a little bit laggy. Let's add the framerate at the window caption to see what framerate we have. We can cut the old caption from its original place and paste it in a while loop after the clock. To see a framerate, we change donut text to this line. Get.fps will get the framerate and we will use the format method to show only 2 digits after the comma. As I said in the beginning, it's unlikely to reach 60 frames per second. For now we have only about 8.56 frames per second. We will try to increase it later. For now the rotation part is done. Okay, what's left is to plot ASCII characters according to illumination. First we need to add ASCII chars. We have 12 chars from the dimmest to brightest. Next, let's move to the while loop. Here we have an output list, which fills all screen of our created pixels with blank space. What else we need is to have another list, which will help us to track how close our donut points are to us. As I mentioned in the beginning, we want to plot only the points which are the closest to us. For that, let's have z-buffer list and fill it with zeros. So if we have no point at pixel location, it will be at infinite distance and we won't see anything. After position calculation, we can add a luminance calculation. It calculates like this and has the range from -√2 to √2. Luminance is a dot product of a surface normal, with direction perpendicular to the surface at each point and light direction, and light source, which is chosen to be behind and above the viewer. Knowing the luminance value for each point and that we need to plot only the point that is closer to us, we can write if statement. If 1 over z is greater than the z-buffer value of a defined position, we change the z-buffer value with a new one. Next, we calculate luminance index. We multiply luminance by 8. We do so to get luminance in the range from 0 to 11 as our ASCII chars. And finally, we need to save these ASCII chars to the output list. We can delete the old output line. So here we have a simple list indexing. For the defined position, we check which chart to pick according to the luminance index. If luminance index is greater than 0, so the point is facing us, we leave that luminance index, else we choose 0. And that's it. Before running the code, let's tweak it a little bit. Let's add some lines to pause our donut code. Before while loop, let's add paused equal to false. So if not paused, we update the display. And if we press space key, paused will be not paused, which will make pause to true and will stop updating the display. Let's run and see the spinning ASCII donut. It works, but there is still some problems to deal with. First, frames per second is very low. And another thing is that if we pause the donut, we can see some pixels showing not the right ASCII values. It doesn't look like they are supposed to be dots. It could be for several reasons. One of it, no closer point from our donut is projected to our pixel screen and we have only from the back, which normal vector is pointing from us, making it the darkest, so why it's a dot. Our created donut doesn't have enough density of points to be projected on every pixel. It could be several combinations between donut creation and its projection. Let's go to the top of the code and at first change the size of the screen to smaller. Let's run the code now. Frames per second improved but very little. To improve more, we need to have fewer donut points resulting in fewer calculations. Also, we still can see the bad projection. Let's try changing K2 parameter to a bigger value and run the code now. It looks like it fixed the problem. Next, let's lower the number of donut points by increasing the theta spacing to 10 and phi spacing to 3. Let's run the code now. Frame rate is increased and the donut still looks good. But rotation now seems off. Let's change rotation parameters by lowering them, A to 0.15 and B to 0.035. Now it looks better. Let's smooth the bonus part. In this part we will change the donut color from just white to colorful. We will need a new library called colorSeize. We start by defining the starting hue value of 0. Next, before the text display function, let's create the HSV to RGB function, which will add H, S and V values of color as input, and we return a new color like this. What we need to do is to change the white color in the text display function to our new function with input hue 1 and 1, and add a hue incrementation in a while loop before the display update method. Let's add hue plus equal to 0.005, and that's it. Let's run the code. We created a 3D spinning and color changing ASCII donut. Hope you liked this video. It was quite long, but I think you learned something new. For original code in C and code explanation, check Andy Sloan's blog. If you have any questions, leave them in the comment section. You will find the code in the video description. If you liked this video, please leave a like and hit the subscribe button for more Python videos.